Hello and welcome back to another video. Today we're going to be covering linear differential equations. This is just another format and another method for solving differential equations. In our case here, we want to solve for the explicit solution, explicit meaning y by itself or x by itself, depending on which variable we find to be its linear in. So jumping right into what a linear function looks like, we have our dy over dx plus p of x y equals 2q of x. This is our general form for a linear equation. So the idea is we have to get this equation here into this format, and then we can proceed with the method of linear differential equations. And also some key points with this equation here, we need our d's to match. So this is a d of y on top, matches with our y. We need something like that for it to be linear. This could be a d of x on top and then an x here. Just it doesn't really matter what the variable is as long as they match. Also with terms of y, you can't have this inside like a cosine or a sine or inside a square root. You also cannot have it raised to some power either. It has to be just a y or just an x, and then it has to match again. So moving on, we will go and make this equation into this format, and then we can proceed with linear differential equations. So starting off, I'm just going to rewrite my y prime as a dy over dx minus 3 equals to a 4y. Now, if we look here, we have a dy dx and a y on this side. I'm going to guess it's probably linear in y, so I'm going to move this over and then this over, rearrange a little bit. So in doing so, I get a 2x dy over dx. I'll have a minus 4y. It's equal to a positive 3. Now, if we also look at our general form, we cannot have anything in front of dy over dx, so I need to get rid of this 2x. So to do so, I'm going to divide everything by it. So getting rid of that, we now have a dy over dx minus a 2 over x times a y equals to a 3 over a 2x. And if you look here, we have our dy dx, nothing in front, that's good. We have a y by itself, nothing there, that's good. No y's on the other side, that's great. So this is in fact linear in y. So what we do next is what's called an integrating factor. Sometimes denoted as IF. That's how I've seen it abbreviated in the past. And the format for this will be rho of x is equal to e to the raised to the integral. So this is inside the exponent. And then we're going to do p of x dx. And this p of x comes from this bit here. So whatever's in front of your linear variable, that's what goes inside this little integral. So in our case, this will be a minus 2 over x that goes in for p of x. So plugging that in, we have e to the integral of our negative 2 over x dx. And we can pull out the negative 2 because that's a constant. And then if we integrate, we get e to the negative 2, so that stays, and then we have a natural log of x. And to get rid of these, we want to move this up to the exponent power. So now we're just left with e raised to the natural log of x to the negative 2, and e to the natural log will just cancel out. So therefore, our rho of x is equal to x to the negative 2. So we want to take this now, this is our integrating factor, remember, we want to take this, and we want to multiply our entire equation by that. So in doing so, once we distribute everything, we'll have an x to the negative 2 dy over dx. Then we'll have minus 2 over, this will be x cubed, because remember this is essentially 1 over x squared. So by multiplying that through, I can just make it x cubed. And then this will also be equal to 3 over a 2x cubed. So once we have this, the left-hand side will reduce nicely. So this is the derivative of the product of two functions. So it'll look like this. In our case, we have d over dx, because that's what's on the bottom. And then we want to take our integrating factor. So we have our integrating factor as one of the functions, and then the other one will be our linear variable, which here was y. Remember, we had our linear variable, linear in y, so that'll be inside here as well. And that's just equal just to the right-hand side, So we have 3 over 2x cubed. And now we want to integrate because we want to get rid of that. So I'm going to multiply my dx over. And then I have d of x to the negative 2y over 2x cubed dx. And now I want to integrate. The nice thing is the left-hand side will always cancel, and you're always left with what's in the what's just inside in the middle here. So you have an x to the negative 2y is equal to. Okay, so now we're going to integrate this bit here. And to do so, I want to rewrite it to a more familiar form. So I'll have the integral of 3 over 2x to the negative 3 dx. I can pull out my 3/2. I'll have x to the negative 3 dx equals to x to the negative 2y. Move that up a little bit. So next I want to integrate here. So I will have x to the negative 2 times a 1/2. That'll be a negative as well. Because if we bring down the negative 2, that'll go away. And we're left with the negative 3. So I have a plus c. And don't forget that our 3/2 stays. Once we have this, we will simplify this. So we have an x to the negative 2y is equal to 3 over 4, and that's a negative, remember, so then we have our x to the negative 2 plus c. And we want the explicit solution, which means since it's linear in y, we want to find y by itself. So going down here, we want to simplify and get this by itself, which is pretty easy to do. We'll subtract or divide by the negative 2. Y equals, and nicely enough, these two will cancel out. So we have a negative 3/4 plus c over x to the negative 2. And then that is our explicit solution. Also, I wanted to note why, when we integrate here, why we don't have this plus c. The reason there's no plus c here is if we have this, and it'll just become e to the c. So if you, for instance, if you had a, we would end up with an e to the x to the negative 2 plus an e to the c. This just becomes another number. And then once we multiply the entire equation by our integrating factor, you're going to multiply everything by that c, which means we can just divide everything by that c, so it's gone. So you really don't need to worry about a plus c, so it's best you don't even need to put it for the integrating factor. Only when you're just doing your final integral will you need to do the plus c. Alright, jumping into our next example. This one's a little bit more complicated, but again, same basic concept. We want to find the explicit general solution of this equation. And remember, this is our linear series, so we're going to do dy over dx plus a p of x y equals to q of x. And so to find this, we need to get y prime by itself. So starting off, I'm going to factor that out. So I have an x squared minus 3 y prime. And then I'm going to move this to the other side because I just want y on the one side. And the reason I moved this over is because we have some function of x over here, but all we have is just the y here. So I want to make sure we just have the y in case it's linear in y. So that's what I'm going to try and look for. So next step is to divide. We want this y prime term by itself based on our general form. So we need to divide everything by x squared minus 3. And then we are left with a dy over dx plus 4x over x squared minus 3y, 12x over x squared minus 3. And in fact, this is linear in y, because there's nothing to the power, it's not inside something else, and then we have our dy on top. So it matches the form, so we are linear in y. That's good. Now we can go on to our integrating factor. And our integrating factor, again, is rho of x equals to e to the integral of p of x dx, where p of x is what's in front of our linear variable, which in this case is this bit here. So we're going to plug that in. So we have rho of x equals e to the integral of 4x over x squared minus 3 dx. And we're going to have to use a u sub for this integral. So I'm going to write this just off to the side here. So if I let u equal to x squared minus 3, my du becomes 2x dx. And replacing the stuff here, we have e I'm going to split this into a 2 times 2. So I have a 2 times 2x. And then I have, let's see, u is equal to x squared minus 3. That's in my bottom. So I'm going to have u on the bottom now. And then I have a dx. And if we take our 2x dx now, because I just split that to a 2 times 2, which is still 4. If I take that, that's equal to du. So now I can replace that with a du. So I have e to the integral of 2 over u du. I can pull out the 2. That's a constant value. And then integrating, I get natural log. So I have e to the 2 natural log of u. I want to raise that back up, because by doing so, now I can cancel my e and my natural log. So I have u squared. And if I replace u with my x squared minus 3, I then have x squared minus 3 squared. And that's equal to my rho of x. So now that we have our integrating factor, what we want to do is multiply both sides by the integrating factor. So if I take that, and I multiply by x squared minus 3 squared, and multiply it by both sides and distribute, I'm going to get that I have squared minus 3 squared dy over dx plus a, notice we have 1 on the bottom, we'll have 2 on the top, so 1 will cancel, so we're left with 1 on top. So 4x times x squared minus 3, and then y stays. And then again, 1 on the bottom, 2 on the top, so one of them will cancel out, so we're left with 1 on the top. So we have an x squared minus 3, 12x. Get that on that side. Next up, we want to simplify this. So the left-hand side simplifies nicely to be the product of two functions, one of which is your integrating factor. That's your first function. The second one will be your linear variable, which in this case is y. So to do this, we have the derivative of those two functions. So we have our integrating factor, x squared minus 3 squared, and then our linear variable, y. This will be equal to the right-hand side. And then next, I want to get rid of this, so I'm going to need to integrate, so I'm going to multiply my dx over. And then I want to integrate this, so I will clean this up real quick. Integrating. So for the left-hand side, it's pretty easy. This just cancels out, and we're left with an x squared minus 3 squared y. And then on this side, we're going to have to do another u substitution. So I'm going to let u equal to an x squared minus 3 again, which as you can see here, our du again will be the same as before, 2x dx. So if I plug u in for this, I have a u, 12x dx, and if I split my 12, 6 times 2 is also 12. So if I pull out a 6, so I'll have 6 integral u of 2x dx, and then if you notice that is du. So I have a 6 integral of u du. This is equal to the left-hand side, which stays the same. And then if we integrate, we get 1/2 u squared times our 6 plus a constant now. And then that's equal to our left-hand side. And if I clean this up, and plug u back in, so 3 times our x squared minus 3 squared plus c. And then we want to get the explicit solution, remember, which means we want our linear variable by itself, in which case we are linear in terms of y. So I want y by itself. To do so, just simply divide over. Okay, and then those cancel out, so we have y equals to 3 plus c over x squared minus 3 squared. And then that is our general solution to this problem.